what we're going to be talking about is relative extrema. Relative extrema is referring to things that we would in normal everyday English call maximums and minimums. And the way that we're going to start this is we're going to begin with an application problem. So suppose that we have the manufacturer of a diet soft drink, and they have spent a lot of money on a commercial to advertise their soft drink. They made some 30-second television commercials, and they were disappointed because the commercials were expensive and it didn't really increase their sales that much. So they were trying to figure out, the commercials were supposed to have been well designed and all that. So why did we spend this much money on these commercials and it's not working? And the company's market research analysts thought that the problem was in the timing of the message of the commercial. Because every commercial has a message, that central thing that they flash at you in the big letters, this is what we want you to buy, this is what you need, call now, call now. And, we all know how we feel about commercials anyway. So basically the commercial's message was drink sparkling light. That was their product that they were trying to sell. And the problem that the research people said there was that either that message is coming too early in the commercial, where people have really not disengaged from the program they're watching and actually started paying attention to the commercial yet, or it's happening too late. People have realized, oh, this is a commercial, flip, get up, go to the bathroom, go, do something else, or just zip right through the commercial. So they want to hit that message coming before, when their interest is there, when they've actually focused on it, but before they leave. Okay? And they found out by watching people watching these commercials, they found out at what point different people engaged. And they came up with a model that says that the viewer's attention span is a function of time, and on the time from 0 to 30, because it's a 30-second commercial, that the function of their attention as far as time, that it follows the equation negative 3 over 20 times t squared plus 6t plus 20. And they want to know when would be the best time to present the commercial sales message. So you don't want it when their attention span is low, and you don't want it when you do want it when their attention span is increasing. You need to know when it's increasing, because at some point there's going to be a maximum attention placed, and then they're going to start not paying attention again. So what we want to find then, that best time, is going to be the maximum value of f of t. And you can see that that's a quadratic equation because it's got a t squared in it. It's going to open down because the coefficient of t squared is negative. So if it opens down and t squared is negative, what happens with it is from 0 to some point, their attention span is going to increase. It'll be increasing higher and higher and higher. But at some point, their attention span will be maximized, which is where we want to know where that is, and then it's going to start dropping off. It's going to wane again. So in order to do that, what we learned in the last section was that we can take a function and figure out where it's increasing and where it's decreasing by taking its first derivative, because its derivative is a rate of change. And when that rate of change is positive, the function is going uphill. And when that derivative is negative, then that function is going downhill. And the way that we did that was we used the derivative and set it equal to 0 to find what we call the critical number. And I think I told you last week the critical number is going to be very important in this section. It's going to give us some really important information. So what we're going to do then is we're going to take that function, which I copied here, I don't know that there's anything I can do about some of the blanks. We'll just just kind of stuck. Time change has caught up with us. So we'll manage the best we can. So there's the function that we're interested in. The first thing we're going to do is we're going to take what's called the first derivative. And the reason I use the term, you're going to see it in your book, the first derivative test, we're not covering section 13.3, but there is also a second derivative test, which is, a second derivative is the derivative of the derivative. Now, with some functions, actually when I've taught that section before, people kind of liked some functions because they could actually keep taking derivatives till the whole function would just disappear. There would be nothing left, and they felt like that was some kind of revenge. I know I felt that way when I took calculus. Okay, you know, I hate this stuff, but by George, I killed that one. But we're only going to do the first derivative. Well, and I had to do all the simplifying that I don't make y'all do. But that was because I was a math major, so. My algebra skills were expected to be good. Lord love my little heart. They were for a while.
What did you graduate
I have a master's from ETSU and my bachelor's from ETSU, but my calculus classes were all at Walter State. I'm a community college graduate, just like y'all. And I sat in that evening seat just like y'all are, because I had kids to raise. So f prime of t, we're going to take the derivative. We bring the power down in front. That's 2 times negative 3 over 20 t to the 2 minus 1 plus 6, because the derivative of 6t is 1 times 6 times t to the 0 power, and t to the 0 disappears. And the derivative of the constant 20 is 0, so we don't write it down. Okay? And this is going to be their attention score or attention span at a particular second. So what we do first is, after we take the derivative, we set that derivative equal to 0. So if we multiply this out, we wind up with negative 3 over 10 t squared. I'm sorry, negative 3 over 10 t, because that turns into 1. So f prime of t is negative 3 tenths times t plus 6, and we're going to set that equal to 0 and find its critical number. So then we have negative 3 tenths t is equal to negative 6. Divide both sides by negative 3 tenths. And it would be just fine. I've already been asked this question, so I'm going to go ahead and answer it. It would be just fine, since that's a nice decimal number there instead of a fraction, it would be also just fine to call this negative 0.3 t equals negative 6 and just use the decimals. So whichever way you want to do it. But whichever way that you do it, it's going to come out that t is equal to 20. So what we see here then is that f prime of 20, t equals 20 then, is the critical number. And then the same as what we did last week, what we're going to do is we're going to plot a number line. Let's see, and maybe I can do this up at the top so I can write the final answer at the bottom. So we're going to plot a number line that starts at 0 and ends at 30. Because that's the only domain the function is effective on, since it's a 30-second commercial. And t equals 20 would be about here. And that's the critical value. And I'm going to show you how to go ahead and incorporate the technology from the very beginning to make this whole process a lot easier. Because when you're having to deal with specific numbers and plugging those numbers into the functions or the derivatives, it's easier just to go ahead and have it in the calculator. So we're going to take the calculator. We're going to go to the y equals menu, and I'm going to clear out everything that's there. And our initial function is the negative 3 over 20t. And since we don't have t, we'll use x. And that's going to be squared. Plus 6x plus 20. And then in my second y equals place, I'm going to go and put in the n-deriv, the numerical derivative, and tell it I want the numerical derivative of y1. I don't want to retype the function. I want to use the fact that I've already typed it in once, because some of them are really long and they get annoying to type in. So in order to get y1 in the parentheses, then you hit the vars key, right arrow to y vars, press enter on function, and press enter again on y1. So when you're ready to put in vars, then that's the same key sequence. Now, you got an 84, you got an 84, and yours has the one that looks different. What you do is you do n-deriv, and it's going to pop up that little template. The first thing you type in is an x. Okay? And then, after that, you type in the function, and that's where you hit vars, then y vars, and then enter, and then y1, hit enter again, and it should put it in there. This isn't for checking purposes. We're actually going to let it find the answers for us without us having to do the math. Okay? We're going to let it do what it does best, which is arithmetic. So you've already put in your first x if you've got the 84, and now you've put in the function. So with the 84, those of you that had the actual derivative-looking notation, then you're going to put in another x. Those that have the 83, we're going to put in x twice. It's just a difference in the order of what you enter. Okay? Now, the first thing I'm going to do is going to be to check something, but it's also going to give me some information that I might find useful later. I'm going to go to the window and make sure that it's set up to let me ask for x values. It's not going to automatically populate the x values. It's going to let me ask for specific ones. Then I'm going to go to the table. And I'm going to clear out what's there because that's not necessarily anything I'm interested in. So what I'm interested in is what's going on with that derivative when t is equal to 20 to start with. What happened at the critical value? So I'm going to ask it to tell me the value of the function and the derivative at 20. So it says the value of the function at 20 is 80, but the value of the derivative is 0. Okay? Then we're going to do our test points. Because the way the critical value works is we pick a number to the left of 20, and I'll try 10, or we could try 0, either one. Because the goal here is to find out whether f prime of whatever our test point is it positive or is it negative? So if I plug in 0, then it says the value of the test statistic is 6, which is positive. And that tells me that the function at that point is increasing, okay, because it's positive. It would have been the same thing if I'd asked it for 10 instead of 20. It still gives me a positive answer, okay? So then the other side, I need to test a value somewhere between 20 and 30, or I could just test 30. But I'll test 25. So at 25, it says f prime of 25 is negative 1.5. Meaning it's decreasing, that's right. So it's gone up, and what goes up must come down. Okay? So when you have a function that is increasing, and then it decreases, at some point it stopped increasing and started decreasing, and at that point we reached what's called a maximum. Okay? And notice that if we think about what the derivative means, that top line where it tells us that the critical value of 20, that the value of the derivative is 0, that makes sense because a horizontal line has a slope of 0. So for just an instant, that function stopped changing. It wasn't increasing, it wasn't decreasing. Its slope was 0. That critical value is actually the point we're looking for. So looking at what we've just seen here, what we have determined by doing the sign changes is that not only is t equals 20 the critical number, but f prime of 20 is equal to 0, which we already knew because that's what we set it to be. So the critical number in this case, because the function increased on one side and decreased on the other side of 20, that critical number is also the maximum value. That's where they're paying the maximum attention to the commercial. So what we've learned from this is that in terms of the application, where they should put the message is at exactly 20 seconds in, because everybody's paying the maximum amount of attention at 20 seconds in. So that's where they should put the message during crystal light or whatever it was. Okay? Well, no, you did and you didn't. You've actually asked a very good question. Is the critical number always going to be either a maximum or a minimum? Is it always going to be my extrema? And I'd like to tell you the answer to that is yes, but it's not. It actually sometimes is no. And we're going to look at a couple of examples of that. So then we're going to have another example of relative extrema, and I'm just going to try to explain this one to you without flipping back to the PowerPoint for a minute. We've got a graph here, and you've got that same graph in your notes, you should have. So what we've got is this graph of a kind of a strange-looking function. But it's not the worst one we've ever seen either. And the whole point to this particular example is for you to learn what relative extrema are. Okay? And it's important that you remember this word relative. Relative is the same thing as a local. Okay? And when you think local, you always think close around you. Okay? Local means right where you are. This graph has no absolute minimum. It has no absolute maximum. The reason it doesn't have an absolute minimum is because its left-end behavior there is approaching negative infinity. So it's going down forever. It does not have a bottom. So that's why it has no absolute minimum. Because it goes on down forever. It also does not have an absolute maximum, because this tells me that it's going to continue upward forever. So there is no absolute maximum value either. However, on the part of the graph that we're looking at, it has relative or local extrema. For example, on the interval from negative infinity to x sub 1, here's x sub 1, on that interval, f of x is increasing. Which tells us that f prime of x is positive. And then on the interval from x sub 1 to x sub 2, here's where x sub 2 is, on this interval, f of x is decreasing. Which means that f prime of x is going to be negative. And so what that tells me about the value of x sub 1 is that x sub 1 is a critical value. It is a critical value. And that particular critical value is a local maximum. Or a relative maximum. Those two words mean the same. Basically, it's higher than any of the points around it. Relative to its nearest neighbors, it's on a higher level. Okay? So then we look on the interval from x sub 2 to x sub 3. And on the interval from x sub 2 to x sub 3, we see what's happening is that f of x increases. And not only does f of x increase, but then that means that f prime of x is positive. So that means your derivative is going from negative to positive. And that means that x sub 2 is also a critical value. And in this case, x sub 2 is a local or a relative minimum because it goes down and then back up. So x sub 2 is lower than the points around it. So then the next interval that we're going to consider goes from x sub 3 to x sub 4. And we see that going from x sub 3 to x sub 4, your function is decreasing. Which means your derivative, f prime of x, is negative. So here we're going from positive to negative, and that means that x sub 3 is a critical value. But x sub 3, unlike the others, x sub 3 is a local maximum. Because it went from increasing to decreasing. It reached a top. And then our last interval goes from x sub 4 to infinity. And what we see happening from x sub 4 and on throughout the rest of the domain is that f of x is increasing, which means the derivative, f prime of x, is positive. So our derivative goes from being negative to being positive, and that once again means that x sub 4 is a critical value. And in fact, x sub 4 then is a local minimum. And again, the words relative and local are interchangeable. They mean the same thing. Okay? Do you understand visually what's going on? You go uphill, you reach a maximum, and you go downhill. Increasing, maximum, decreasing. Or you go downhill, reach a minimum, go uphill. Decreasing, minimum, uphill. Now, the thing about this that I want you to pay attention to is there is a derivative associated with this critical value. We can find the slope of a tangent line. And the slope of that tangent line is going to be 0 because that critical value is where the derivative is 0. That means the slope of a tangent line is horizontal. That also happens at x sub 2. We can draw a tangent line that is horizontal, has a slope of 0, and it touches at one point. We can do that at x sub 4. If we draw a tangent line at x sub 4, it will have a slope of 0, and it will be horizontal. The catch is you cannot do that at x sub 3. because all of those lines would be tangent as well as one that might have a slope of 0. Okay? So yes, x sub 3 is a critical value. It is a critical value. And it is a relative maximum. But what I'm telling you here is the derivative may or may not find that value, because the derivative may not have x sub 3 in its domain, because we can't draw a unique tangent line there. Okay? Because remember, back in Chapter 11, we said that the derivative exists as long as the function is smooth and continuous, no holes, but also it only exists if the limit exists, if the function exists, and if the function doesn't come to a sharp point. So there's actually no derivative, just as a reminder, at x sub 3. We can find a value, but that doesn't mean the derivative itself actually would exist at that point. It may not. So all of this leads us to something called the first derivative test. I'm actually skipping through some of these slides to talk to you about the first derivative test. So basically what we see here is we see a picture of a function. And that function shows us that there is a relative maximum because this function increased, reached a maximum, and then decreased. And then this function decreased, reached a relative minimum, and then increased. So this is what we're leading up to. It's what's called the first derivative test. We're going to practice this one more time by looking at a graph that's a different one this time. So if we're looking at this function, whatever f of x is increasing because its derivative is positive. Then, after it reaches a relative maximum, which is when the value of the derivative, f prime, which is its slope, f prime at x sub 1 is equal to 0, which tells us that x sub 1 is a critical value because the derivative is equal to 0 there. And then after we pass the relative maximum, then we see that f prime of x becomes negative. And that's because it's decreasing. The function itself is decreasing. Yes. That's why it's important that we be able to find critical values. So then once it gets so far down, it stops decreasing for just an instant, and its slope becomes equal to 0, which means also that f prime of x sub 2 is equal to 0, which is what makes it a critical value, because it stops decreasing. F prime of x is negative until it gets to x sub 2. Okay? When it gets to x sub 2, it stops going down. It has like a bottom, a floor. So it's going to change directions. And when it changes directions, it goes just for an instant. The slope goes from being negative to being 0, because the only way to get from 0 or from negative to positive is to pass through the value 0. Okay? No. The slope is 0. The slope of that tangent line is 0. Remember, when we're looking at this and this, that's telling us that that line is a horizontal line. It's talking about a horizontal tangent. That's the same thing here. If I draw a tangent at that first critical value, that tangent is going to be horizontal. It'll have a slope of 0, which means your first derivative is 0. Because first derivative and slope are the same thing. So then what we see happening after x sub 2 is the function starts increasing again, which means then that your derivative has gone back from being negative, then being 0, now it's going to be positive. And it does that until it gets to x sub 3. And at x sub 3, it stops for just an instant, and then immediately changes direction. There is no smooth change. It stops like a screeching halt, and then just turns the other way. So the derivative on the other side, if it goes from increasing to decreasing, that makes this point a relative maximum, despite the fact that we can't necessarily draw a tangent line there. It's still a relative maximum. And if you notice here, while this function has no absolute minimum, because it keeps on going down, it does have, because it actually ends at x sub 4, from negative infinity to x sub 4 is its entire behavior. That means this is not only a relative maximum, but this is also an absolute maximum. Because that's the highest that function will ever go. Okay? The word absolute means it will never go past here. It stops. The endpoint is actually a relative minimum. The endpoints are always one of your critical values. If it has a definite endpoint, that's where it's definitely changing behavior because it's stopping. So the endpoint is a relative minimum, and you could have a case where the endpoint would be the relative maximum instead. Instead of going down, it could have gone on up and stopped. Now this is why I was kind of hedging, Chris, when you asked me the question that I knew you were trying to ask. Be very careful that you understand that every critical number of a function is not a relative extrema. There are candidates for extrema. They could be, but they don't have to be. And here's an illustration of one where it's not. This is the function f of x is equal to x cubed. And notice what's happening here. Its derivative, since this is the function, its derivative f prime would be 3x squared. Because the derivative of x cubed is bring the 3 down in front, reduce the power by 1, that makes it 3x squared. And 3x squared is equal to 0. If x squared is equal to 0, which is only going to be true if x is equal to 0, because the square root of 0 is 0. Okay? So that means 0 is a critical point. It's a critical value. But I want you to notice where x equals 0 is. X equals 0 is the point 0, 0. Is that a maximum? No. Is it a minimum? No. It's neither one. In fact, that function has no maximum and no minimum. It goes down to negative infinity and it goes up to positive infinity. And the truth of the matter is that it's increasing as it approaches 0, and as it leaves 0, it's still increasing. So when it increases, hits the critical value, and keeps on increasing, you don't have an extreme point. You have a critical value, because that is where the derivative is equal to 0, but you don't have a relative max or a min. Okay? That's why this is so important. A critical number is a candidate. It's running for the office of extrema. That doesn't mean it's going to win. It is only a candidate. Okay? So that's an important thing to be aware of. So we've talked about now the first derivative test. All of that gives us the first derivative test. And what I want to show you now is a summary of what could happen with your critical values. So if you look at this PowerPoint slide, this is showing you what happens when f of x has a relative maximum. On some interval from a to b, there's a number c that's in between a and b. And if from a to c, the value of the derivative is positive, and then on the interval from c to b, the derivative sign is negative, that means it went from being increasing to being decreasing, and in that case you have a maximum because you go up the hill to the top of the hill before you go down on the other side. And it doesn't have to be a smooth curve for that to happen. Here we can see that on the interval from a to c that the function is increasing, but when it gets to c on the interval from c to b, to the other end, it is decreasing, so it goes up the hill and down on the other side. It's still a maximum value. And in that case, the value of the derivative is going to be positive and then negative. The opposite of that is going to be true on the second row. This function is decreasing from a to c, and then from c to b, it's increasing. So if it decreases and then increases, you've hit a minimum value. You go down the hill into the valley and then climb back up the other hill. The same thing happens with this function. It's decreasing and then it's increasing, so we have a relative minimum. But in this function, the function increases, hits the point C, and then continues to increase. That is not a relative max or min. There's no relative extrema there. There is a critical value there, but no relative extrema. The same thing happens here. It is increasing, it hits C, and then it increases some more. There's no relative extrema at this point C either. It's not the bottom, and it's also not the top. It just changed directions. And the same thing would be true if it decreases on both sides. If it decreases, hits the critical value, and then continues to decrease, it hasn't hit a minimum. It's still going down. And it doesn't matter whether the curve kind of flattens out for a second and decreases, or if it kind of goes vertical for a second. and decreases. Either way, there is no relative extrema there. There's no relative max, no relative min, even though it is a critical value. Okay? And you should have this sign chart in your notes. So what we're going to do now, this is actually pretty much the rest of section 13.2, is we're going to do some examples, and I'm going to have you use technology to do these. Okay? So the first one that we're going to do is f of x is equal to 2x cubed minus 3x squared minus 72x plus 15. And yes, I know that it's not that hard to do this derivative and set it equal to 0. So we're actually going to do it on the first one, but then we're going to check it with the calculator. On the second one, we're going to look at the second one and say, you know, we can do it, but the calculator's faster. So this is kind of a lead-in to how we're going to do these problems. First step, find the derivative. Find f prime of x. And since the function itself is 2x cubed minus 3x squared minus 72x plus 15, the derivative of 2x cubed is 3 times 2 is 6, x to the 3 minus 1 would be squared, minus 2 times 3 is 6, x to the 2 minus 1 is 1, so we don't usually write that 1 down, minus 1 times 72 is 72, x to the 1 minus 1 is x to the 0, and that's 1, and we don't generally write that down. And then the derivative of 15, of course, is 0. So here's our whole entire derivative. Step 2 says set the derivative equal to 0. And then you have to solve for x. Now you have two options on solving for x. You can factor, and this one actually factors, and it's pretty easy. Or if you can't factor, we can always use the quadratic formula. I don't care how ugly those numbers get, they always plug in for A, B, and C. And we do the arithmetic, so that's not going to be bad. But since this one factors pretty quickly, I'm going to go ahead and factor it. So if I divide every term by 6, what I have is 6 times x squared minus x minus 12 is equal to 0. And that means that that's only going to happen, since 6 is not equal to 0, that's only going to happen if x squared minus x minus 12 is equal to 0. And x squared minus x minus 12 is the product of x minus 4 and x plus 3, because negative 4 times positive 3 is negative 12, and negative 4 plus 3 is the negative 1 in front of that middle term. And since one or the other of those has to be 0 for their product to be 0, then I know that x minus 4 equals 0 gives me x equals 4. And that x plus 3 equals 0 gives me x equals negative 3. So those are my critical values. I know what my critical values are now. So what I want is I want to make my number line and do my sign test. So negative 3 is over here, positive 4 is over here, 0 somewhere in between them. And then a number on the other side of 4 might be 5. You could actually pick anything you wanted to, but 5 is one of the easier ones. We don't pick ugly numbers if we can pick nice numbers. And then something to the left of -3 might be -4. So those are going to be our test points. And we need to know if those are positive or negative, because we know what these critical values that the critical values gave a derivative that was 0, a slope that was 0. So to let our calculator help us as much as it can, I'm going to go back here to y equals. And I will tell you that one thing you might want to do from here on out is to leave strictly y2, saying that it's the derivative of whatever's in y1. Then you can just go back and change y1 however many times you want to. That way you don't have to type in a lot of extra stuff. So in this case, my y1 is 2x to the third power minus 3x squared minus 72x plus 15. And then y2 is the derivative of that function, and I don't even have to actually type in the derivative. The calculator will find it for me, or at least it should. So then we'll go to the table, and the first thing I'm going to do is check and make sure I got my critical values right. So I'm going to ask it, by the way, what is the value of the derivative when x is -3? Since that's one of my critical values. And it says out here, well, the value of the derivative is 2e -6. Now, if I round that off to, say, 3 or 4 decimals, what is e -6? 0. So essentially, then it's saying, yes, your critical value gave you a value of 0 in the derivative. Okay, the other critical value is 4. And it tells me, yeah, okay, then the derivative is 2e -6. 2 times 10 to the -6 power. Take that 2 and move the decimal 6 places so that it becomes in front of the 2, and it becomes decimal 0.000002. That's close enough to 0. Now, the fact that I got these other two numbers in y1 shouldn't bother you, because if you're going to have to graph it by hand, that gives you 2 points on the original function. So what y2 is telling you is that this is an extreme point, and that might be a maximum, and this might be a minimum, given... Step 3, use your calculator to, what we're actually ultimately going to do is use it to evaluate this. But as a first part of that, we're just verifying, actually, that we do have the right critical values. The slope really is 0 there. Since the calculator is so good at arithmetic, then we don't have to worry that we might have made a mistake. Okay? So then one of my test points has to be to the left of -3. So maybe I'll use -4, like I said on the number line. So not really interested in what the value of the function is at -4. I'm interested in what the derivative is at -4. And the derivative at -4 is positive. It's not the fact that it's 48, it's the fact that it's positive. So that tells me that at this point the function is increasing because the derivative is positive. So then I move to my next test point, which is 0. And that -72 out there tells me that the derivative is negative. It's not the fact it's negative 72. It's only the fact that it's negative. So that tells me that on this interval, my function is decreasing. And it decreases all the way until I get to positive 4. It continues to decrease. So then my next test point is out here at x equals 5. So when I plug 5 into the derivative, not the function, but into the derivative, which is what's out here at y2, I see that f prime of 5 is positive, which tells me that it's increasing on this interval. Okay? And because of all of that, because I'm going from increasing to decreasing, that tells me that negative 3 is a maximum. Okay? And that point where there is a maximum value, if you go back up here, and this is why making it on the calculator is so handy, that point is actually negative 3, 150. Because the calculator already calculated it for you. I also know that on this side it's going from decreasing to increasing, which tells me it's doing this. And that tells me at that value 4, I have a minimum, a relative minimum. And that actual relative minimum point is 4, negative 193. So I have a pretty good picture of what that function looks like. Bless you. So in fact, I can draw a graph of that function without too much trouble. See, I don't have it there, but I do have a graph of it. Or we could draw it on the calculator with what we know. I think it's in the PowerPoint. So there's a graph of the function. And notice here's my maximum value, negative 3, 150, which is what we were looking at on what we drew. And it decreases all the way from negative 3 until it gets to 4, and then it hits a bottom, a relative minimum of 4, negative 193, and then it goes back up again. And you would have been able to use the calculator if you were trying to draw it by hand to add some points to that, not just the maximum and the minimum, but you also know that at the value negative 4, the y value of the function is 127. So this next point down here should be at about 127, which looks about right. And we know that at 0, it crosses through 15 on the y-axis, so there's the point 0, 15. And here's the point 5, negative 170. Right about there. So if you were trying to sketch this graph, knowing those numbers off that table of values would be helpful. It would help you draw a sketch of your graph. If you want to draw the graph and verify it on the calculator, what I would suggest you do, unless you just really want to wait forever, is you turn off your derivative function. You can leave it there, but you turn it off by putting your cursor on the equal sign and pressing enter. And then notice from our table that the numbers that we used didn't range very far from 0. So we could actually just use, for example, on the x values, we could use -5 to 5 if we wanted to. And then go zoom and choose 0, zoom fit, or you can set the window knowing what you know from your max and your min. It needs to go up to at least 150 or more because that's the maximum, and it needs to go down to about -200 because the minimum is for -193. And then your calculator gives you all the rest of the information you need to be able to draw a good graph. But all we really need to do this for is to verify what we found. Okay? Now, if you look in the PowerPoint, I'm not going to go through this with you, but if you look in the PowerPoint, it tells you that you can use your graphing calculator to find the maximum and the minimum using the Calc menu, which we did in Math 1630. We'll learn how to find maximums and minimums of functions by using the Calc menu. You should have. If you don't, I'll put it up. You may not have the whole PowerPoint. What you probably have is a PDF of it. So if I want to find the... hit the wrong thing. If I want to find the minimum, I can see visually there's a minimum somewhere around here. So I'll trace my cursor over pretty close to it. And hit enter, and then trace on past it. And hit enter again. And it tells me that that's the minimum value for -193. And the same thing on the maximum. The thing is, you've got to remember that you have to start to the left of what you're looking for. You have to start below it, not above it. So I know that function has a maximum that's between there and there. And it comes back and says, yes, there's a maximum at -3, 150. Aren't you wore out?
Yeah. Is he here?
No, he finished.
Oh, did he?
Yeah.
Oh, Jim Cumberland. Yeah, we've got.
Okay, take my key and I'll off so you get the rest of your stuff. I forgot to give it to Merle. Okay. So does that make sense so far to everybody?
So what you're saying is all that other beautiful function stuff that we've done, you know, you can just sit there and put it in the calculator.
Unless I tell you to use to show me the sign change chart.
Oh, please don't do that.
No, I might be that mean because it's not hard to make that sign change chart. You can get the calculator to do it. No whining. This.
Doing all that.
This. Take the derivative, find your critical values, then look to see on your test points, is it going up or is it going down by using your derivative. Okay? Not necessarily. If I ask you to graph it, it helps you to graph it, but unless I ask you to graph it, you don't need to. Okay? Most of the focus is on being able to find this stuff without graphing it, because that's not necessarily the important thing. When we get to the applications, you'll see that. So here's our next example. And we're going to use the calculator for the example. So the example says 6x to the 2/3 minus 4x. And I turn the derivative back on. Now, this one is not particularly challenging to find the derivative. It really isn't. But what you're probably going to find a little more annoying is having to set it equal to 0 and solve it. So if this is the function, f prime of x, the derivative, is going to be 2/3 times 6x raised to the 2/3 minus 1 power minus 4, because the derivative of 4x is just 4. And 2/3 times 6, either using the calculator or doing it with arithmetic, turns out to be 4. And 2/3 minus 1 is negative 1/3. So there's step 1. The derivative is 4x to the negative 1/3 power minus 4. Step 2 says set that equal to 0 and solve it. Which leads you to there. Now there's at least 3 ways. If I gave it to 3 different people, they would tell me all 3 of these different ways, I'm sure, to solve this problem. There's at least 3 ways to solve that algebra equation. Not all of them are necessarily easy. Although the answer to this one in particular is not hard. But it could be very ugly if it weren't for the way that it actually comes out. So the first way would be to add 4 to both sides. Usually this is the stage where most everybody that's not comfortable with negative exponents wants to change it back into a radical. There's an easier way, but this is where most people just want to change it back into a radical. So if you're going to change it back into a radical, you're going to have to remember that it's a negative exponent, so it's going to go in the denominator, and that a 1/3 is a cube root. And then you're going to want to put that 4 over a 1, because the easiest way to solve this problem is to cross multiply. Because what that takes you to, then, is this. 4 times the cube root of x is equal to 4 times 1, which is 4. And then you divide both sides by 4. And that leaves you at the point where you can actually answer the question pretty easily if you don't think too hard. If you think too hard, you're going to make it hard. and that's a cube root. I forgot my 3. So what's the cube root of x? What is x if the cube root is 1? 1. Okay, it's 1. If you want to do it an easier way than that, just remember that whatever the index on the radical is, raise it to that power on both sides. The cube root of x cubed is just x. And 1 cubed is just 1. Okay? Now remember, there's actually 2 critical values. It's not just the one where you set it equal to 0. You also have a critical value where the derivative fails to exist. And there is a number where the derivative fails to exist. The number where the derivative fails to exist is at x equals 0. And the reason for that, if you'll think about what this says 4 over the cube root of x minus 4. When will that fail to exist? Even if we let it be equal to 4, when is this going to fail to exist? What value of x can we not have where you see it? What can you not divide by? 0. So what is the cube root of 0? 0. So you cannot have x to be 0 in this problem. It is not in the domain of that derivative because that negative exponent puts the x in the denominator. So you have to worry about dividing by 0. So x equals 0 is also a critical number. Because f prime of 0 does not exist. X doesn't work in that derivative. X equals 0 doesn't work in the derivative. So now we have our 2 critical values. Now that we have the 2 critical values, all we need is the sign chart. So we have a critical value of x equals 0. And we have a critical value of x equals 1. And the reason those are critical value is that f prime of 0 is undefined or does not exist, and f prime of 1 is actually equal to 0. So we're looking for where the derivative is either 0 or it doesn't exist. So on the calculator, we've already put in that function. We left the other one. So we're just going to go to the table, and I'm going to clear out what's there so we can just look at what we want for our new function. So the first thing we say is, okay, what is f prime of 0? And the calculator lies. It tells us it's negative 4. Okay? Math 8, then vars, y vars, function y1. Chris, do you use a TI 83 or 84? Okay, then. So this is Math 8. And then in order to get y1, you press bars, then right arrow, and then enter, but you hit the enter button twice. Okay? And then you know where your comma is. You know where the X is. So you put comma, X, and then you've got to remember to close the parentheses. Okay? That's how you get it in there. So when I plugged in 0, it doesn't confirm that the derivative doesn't exist there. It says, oh, it's -4. No, it's not. Did I put the function in wrong? Okay. Uh-huh. No. Right. All of them would end up with x equals 1 being the only critical number. And that this tells you that's in the denominator, so x can't be 0. Because it doesn't matter what power you raise 0 to, it's still 0. And if it's in the denominator, it's still undefined. It's not going to exist. Okay? And that's going to be true in every single one. This one only produces x equals 1 because the derivative does exist at x equals 1. But if you remember, I warned you that sometimes your calculator lies about the value of the derivative, which is why you need to know how to do it both ways. Okay? So it didn't confirm that f prime of 0 doesn't exist, but that's okay. We know it doesn't, and we know why it doesn't. It's still a critical number. The other critical number is 1. And it does indeed confirm that the value of the derivative at x equals 1 is 0. Okay? So then we're going to do our test points. So we need to pick a test point in each interval. So for 0, from 0 to negative infinity, I'll choose -1. And for 1 to positive infinity, I'll choose 2. And then between 0 and 1, it really doesn't make any difference what I choose. I'm going to be stuck with a fraction no matter what. So I'll just choose the easiest one I can think of, which is 0.5. Because that's easy at least to plug in on the calculator. So using my test points now, my first test point is -1. The value of the derivative is negative. That tells me that the derivative is decreasing until it gets to x equals 0. Because the derivative is negative, it has a negative slope. My next test point is 0.5. And that turns out to be positive. Doesn't matter that it's 1.0397, it's positive. So that tells me that from there up it's increasing. And it increases until it gets to 1. So then I use my test point f prime of 2. And looking out here at the last column, it says the derivative is negative. It's not the value of the derivative that you care about. It's only the fact that it's negative. Because the fact that it's negative tells you the function decreases. Okay? And given that I don't need to go much outside the origin for the domain, I go over here and look at the window. So if I go from -5 to 5, I probably will see everything I'll ever need to see. The question is, what do I need to set my y's to? For that, I need to go back and look at my table. My table says that my y values, if I used -1, I got -8. I'm sorry, if I used -1, I got 10 for the derivative, so it's going to have to go up to 10. It doesn't look like this function ever is negative. Looks like it's all above the y-axis, because all the y values that I'm seeing here are positive. I know that it's going to go, if I'm reading it to the left, it's going to approach positive infinity. It's not going to have a maximum. And it's going to touch down here and then go back up. So it's not going to have a minimum. This probably is a minimum point, and that probably is a maximum point because it goes up and then down. That's a max. Down and then up, that's a min. So that tells me it's likely not going to go below the axis. So if I set my window up, I'm just going to go down -2, so just in case it does something I don't think it does. And then we'll go up to about, I don't know, about 12. Let's see what happens. Oh, I forgot to do something. I'm surprised it graphed that fast. It's still graph, okay, and that, when it gets done, I'm going to delete that because that's the graph of the derivative. So I'm going to turn the derivative graph off. We only want to look at the function. And if I had been thinking more about what I was doing when I talked about that, I said, you know what, comes down then goes up, so it's hit a minimum value at x equals 0. So locally, yes, that was a minimum value. But it goes up and then down, so it hits a maximum at 1, but then it's going down forever after it reaches 1. So I was wrong to think that it wasn't going to go negative. It does. Okay? That's why you always want to go a little bit outside just your critical numbers, just in case you missed something. So there's a graph of the function. And that is really, really similar, as a matter of fact, to the graph that they have in the PowerPoint. So there's our sign changes. And there's what the graph looks like. It's really similar to what the calculator looks like. Okay? Same graph. It's the same graph, and it should be in the PowerPoint of your notes. Okay? So this is exactly what we think happened. It hit a maximum at 1, 2. Then it went negative. It took a nosedive. It was decreasing until it got to 0, 0, and at that point, it started increasing again. So the point x equals 0 was your minimum point. 0, 0 is the minimum, the relative minimum. And because it goes up to infinity on one side and down to negative infinity on the other, there is no absolute max or min, but there is a relative max and min. Okay? We have one more example. And that is the example x cubed times e to the x. And as it says, we're going to have to use the product rule. Now, I'm going to show you that we do not have to use the product rule and multiply all this out necessarily. Okay? That first step will do just fine. So here's our example. And as I said, it is a product rule because it's actually x cubed times e to the x. Make that multiplication really specific. And neither one of those derivatives is a hard derivative. So the way you do product rule is you take your x cubed and you multiply your x cubed by the derivative of e to the x, and the derivative of e to the x is e to the x. And then you add. And then you take your second factor, which is e to the x, and you multiply by the derivative of x cubed, which is 3x squared. And it is beyond me why they feel like they have to factor out that e to the x. I would just leave it alone. Of course, then again, I'm not going to try to set it equal to 0 and solve it. I'm going to let the calculator help me find it. So there's your derivative. And what you want to know is, when is that equal to 0? And there's 2 or 3 different ways to do it. But one of the ways, to me, is actually the easiest way. What if I just subtract e to the x times 3 to the x squared from both sides? And if I do that, I wind up with one expression is equal to the other one. Is there a common factor on both sides that I could divide out? E to the x. And that leaves me with x cubed is equal to negative 3x squared. Now, at that point, I do kind of have a problem.
Shouldn't that be like equal to 1? That's the derivative of that.
No, it's not equal to 1, because 1 cubed would be 1, and negative 3 times 1 squared would be negative 3. We're looking for where they're equal to one another. Now, algebraically, that's not easy to solve in the form that I put it in, but it's easy to solve if I do this. In fact, what I'm doing is undoing what I did to start with to get rid of the e to the x. I have an x in both terms. And actually, I could have done it right here. That would have taken this down to what I'm going to get over here, which is x squared and 3x. And I would be trying to find out where is x squared equal to 3x, which still might not be much fun. But if I have x squared plus 3x is equal to 0, I can solve that quickly. All I need to do is factor. Okay? X times x plus 3. And that's equal to 0 only if either x equals 0, there's critical value number 1, or if x plus 3 is equal to 0, And that means x is equal to negative 3. There's critical value number 2. So for those of you who are algebraically talented at solving equations, there is a way to do it algebraically. You could, which makes you algebraically talented. Yeah, actually, yeah, it should be, yeah, and it is negative. I forgot that I was bringing it down from there, so that negative sign follows it. So yeah, it would still be negative 3, so you still get the right answer. So you can solve it by factoring. You can use any number of algebraic manipulations to get where you're going, or only if x is equal to 0. Only if x is equal to 0, because e to the 0 is like anything else to the 0, it's 1. Okay? E is the natural logarithm of 1. So what I'm going to do is I'm just turning off those top two equations. I don't want them to show up in what I'm about to do. What I could do is I could take this equation right here, and I could put the left-hand side into y3 and the right-hand side into y4, and just go to my standard window, my negative 10 to 10 window, which is going to be way bigger than I need. And right in here, I see that they cross in two places. So I'm going to shrink my window down. Oops. Shrink, not increase. So that I'm seeing just around the origin, because actually I could have predicted I didn't need to. Let's see, I do think I need to go further than negative 2, or I won't get my critical number. So let's go from negative 4 to 4. And hit graph. So we see pretty much right in around the origin. And what I see is that there appear to be two places where that thing intersects. It might only be one, but it appears to be two. If I make the window a little less tall, I didn't make it any better. So what I want to find is the intersections. This is one of the intersections is at 0, 0. Now, if I'm not sure that that's the only one, all I have to do is go do the same thing again and have it actually start there. Well, let's see. No, I don't want to have it start there. I want to have it end there. Is have it start at a more negative place, like, where'd you come from? So it looks like what it found was right there. I'm wondering what it's going to find over here. So I'll let it guess from that side and make sure it hits the first one. And it found negative 3. So if you think there's 2, but you're not sure because the graph's so little, go way to the left of where it seems to intersect, and it'll find the first one, then go way on the right of the intersection, and it'll find the second one because it finds the ones that it's closest to. If it finds the same one both times, there was only 1. Okay? So you could use your calculator to find that. That was the point. So now that we've got the critical numbers, all that we need to do is do the sign changes, and we're good to go. And the calculator is going to handle all of that for us. So x equals 0, x equals -3. Those are our critical values. Probably one's a max and the other one's a min. Probably. The way we verify that is we pick numbers in each interval. We're going to find f of -4, f of -1, and f of 1 and see what the signs are. And we're already set up to do that. All we have to do is change our function. So our original function was x cubed times e to the x. And the table says at f of -4, at f prime of -4, let's see, I left my derivative turned off. So at -4, the derivative is negative. It's going down. At -1, it's positive. So it's going up. And at 1, it's positive. It's going up again. So what that tells me, since we're going up, and the critical value that's in that interval where it's going up is that 0 is a critical value, but not an extrema. It's not a max and it's not a min, because it's going up and going up. But it tells me also, since around -3, it's going down and then going back up, -3 is a minimum. Okay? So there's your pattern. Negative, positive, positive. Okay, and that's actually what the graph looks like right there. Now, if we were going to graph it, we would just use the calculator. Okay?
I understand now. Like, give us an extra week.
Mm-hmm.
Oh, man.
Now, the only way to learn how to do this is to practice. And what you're practicing is taking derivatives of functions and then finding out how you can find where the zeros of the derivative are, because that's your critical values. And then you plot those critical values on a number line, and then put test points between each of the critical values to know if the derivative is positive or if it's negative. And remember, if it goes up then down, it's a maximum. Down then up, it's a minimum. Up on both sides, nothing. Down on both sides, also nothing. It's not an extrema. Something weird's going on, but it's not an extrema. And you'll notice what actually happened here, because 0 is one of your critical values. Notice what happened is that's actually what's called an inflection point. And that's what the second derivative test that I mentioned to you is for. What you do in the second derivative test is you take the derivative of the derivative and set it equal to 0 to find out where there's an inflection point, because it'll tell you the derivative was equal to 0 at the second derivative being equal to 0. It'll tell you that it actually flattened out for an instant. But we're not going to do the second derivative test. We don't need to know how to do that for anything else we're going to do. Okay? So the last thing we've got is an application problem, and then we'll talk a little bit about 14. But I want you to take a break, get up, and walk around and get the blood flowing. I think that's necessary. So let's pause. That I didn't. You'd think that big red pause would hit me right in the face. So this is your cost function in terms of Q bicycles being sold. This is your price function. Price function is always a function of the demand for those bicycles. So this is the price for Q bicycles. And they're asking us about revenue. So the first thing we need to do is we need to figure out what is the revenue function. What does the revenue function look like? And since Q represents the number of bicycles, we'll use R of Q. Revenue is always how many did you sell times the price. Now, I'm just going to use the words, price. Q is how many did you make and sell, but P is the price. Okay? The price is the function D of Q. So the price is 90 minus Q. This is where people get mixed up a little bit. Q is the quantity. The price that you sell it for turns out to be 90 minus the quantity that you made. Little p stands for price. Big P is profit. Little p is price. Okay? And they always do it that way in economics and in math books. Big P is always profit, little p is always price. Okay? But price is always a function of the demand. Now you can switch it around to where demand is a function of the price, and sometimes they do that, but if they give it to you in terms of the price as a function of demand, it's easier just to go with it that way. So we're not worried about profit yet. We're only worried about revenue. So the revenue, which is R of Q, the revenue from Q bicycles, is the number of bicycles times how much did you charge for each bicycle. Okay? So that means your revenue equation is 90Q minus Q squared. And I'll check back here for the units because we need to know the units. And it doesn't say that it's in dollars, so I guess we're just going to assume it's in dollars. Probably not. Probably not.
Are there going to be a lot of questions like there were a few moments ago?
I will probably ask you to give me some straightforward derivatives, because you need to remember how to do derivatives, and if I don't keep asking you, you'll forget to do them. then I'll probably give you some functions like the ones that we did here for our examples and ask you, find me the critical values. Tell me if the critical values are relative max, are they a relative min, or are they nothing, just critical values. So some doing just what we did tonight. And that actually encompasses what we did in 13.1, because in 13.1 we were taking the derivative and looking to see when was it positive and when was it negative. So 13.2 is really just an extension of 13.1. So here's our revenue in dollars.
It doesn't. Really, other than the application problem, it doesn't. So this is dollars for selling Q bicycles. And we want to find the maximum value of, which means we need to find out, because we're looking for maximum, and that maximum occurs where R prime of Q would be equal to 0, because that's what tells you you've got an extreme point. What we do is we're going to take R prime of Q. So since this is R of Q, we need R prime of Q. So the first thing we do is take the derivative, just like we did for the other problems we did. So R prime of Q would be 90 minus 2Q, because it's the derivative of this. And the derivative of 90Q is 90. The derivative of Q squared is 2Q. And then our second step is set R prime of Q equal to 0. And then we solve to find the critical value. So we're getting critical value, CV. That means 90 is equal to 2Q. We just add Q to both sides. And then we divide both sides by 2. And that tells us that Q is equal to 45, and that is your critical value. Okay? This problem is actually easier than ones we did before. Once you get the revenue function, the hard part's usually the revenue function. So the critical value is 45. We're going to draw the number line. The number line actually does not go to infinity, because the least number of bicycles you can make is 0. And theoretically, you could make an infinite number of bicycles, but I'm sure you're going to be limited by resources and things like that. But since we don't know what those limitations are, we're going to go from 0 to 45, which is your critical value. And then we need to do exactly what we've done before. We're going to test a number on sides of 45. And you can test anything you want to on either side. It's up to you. We could test a number close to 45, or we could test a number all the way down here close to 0 and just test R prime, because it's to the left of 45, and it's easy to plug in. And if you want one that's not too big and is easy to plug in, we could plug in R prime of 50, or even just 46. Okay? So we'll use the calculator, just because it does arithmetic so nicely.
So our actual function, our revenue function, because that's what we actually put in Y1 is the original function, is 90x subtract x squared. So without having to do much arithmetic, yeah, it came back. I think it's just old and cranky like me. Okay, so there's the first part of the problem. Second one says, find the maximum weekly profit. Okay, now you need to remember what profit is. Profit is the big P. Profit is always revenue minus cost. Now we know what the revenue equation is. there's your revenue equation, 90x minus x squared. Okay? The question is, what's the cost equation? And it's 10 plus 5q plus 1 over 60 q to the third power. So there's revenue. Let me write the cost down, and then I'll show you what I wrote down. So there's your revenue equation. I'm sorry, you're not just your there's your profit equation. The first set of parentheses is your revenue equation. The second set of parentheses is what it told us the cost equation was. So what this tells us is that the profit equation, in order not, we could actually just type all that in parentheses in Y1, and it would be fine. But it'll be a little less typing if we try to collect some like terms. So this is 90q minus q squared minus 10 minus 5q minus 1 over 60 q to the third power, because you're subtracting all three of those terms. 90q minus 5q is 85q. Minus 10 is by itself. Q squared doesn't combine with anything. And then this last part actually is the leading coefficient, so this tells us it's a cubic equation. So there's your profit equation. And we'll type that in at Y1. And we'll use X instead of Q's. Y'all help me make sure I didn't leave anything out. Yeah, there is, because I've got it on my phone. You used to be able to kind of bootleg it, but it's kind of hard to get now. Because I had the free version for a long time, but the one that I got was, it wasn't expensive, like $10, which is way cheaper than a calculator. No, it's not a rented app. It's actually one you can buy outright. Just Google TI-83 or 84 graphing calculator app. Yeah, they're mostly cheap. Okay. Yeah. I let my students use their calculator on their phone until I figure out that they're not being honest. And after that, it's like, put the phone away. You can't use your phone, sorry. Because there's lots of apps that'll solve the whole problem for you. Okay, so what we want to know, now that we have the revenue function, is we need the derivative of the revenue function, and we need to set it equal to 0. Our profit function. I'm sorry, I keep saying revenue. It's profit function. Okay? So in order to find the derivative of our profit function, I'm going to go to the top of the page now. Y'all follow along in your notes. The derivative of profit is going to be 3 times negative 1 over 60 which is negative 3 over 60. And I'm not going to clean that up just yet. I'm going to leave it like it is. Q to the second power minus 2q, which is the derivative of negative q squared, plus 85, because that's the derivative of 85q. And the derivative of the negative 10 is 0. So here's your whole derivative. Now, I can do this two different ways. We can just keep using the negative 3 over 60, which actually is not too bad, by calling it 1 over 20, and it'll turn into a nice decimal for us if we do that. So it's negative 0.05. That might make our life a little easier. And we do that. And the reason I did that is because I don't even want to think about plugging in fractions at this point into the quadratic formula, and you don't either. So the value of A is negative not 0.05, negative 0.5. No, it is 0.05. I'm sorry. I had it right first time. Duh. It is getting late. And the value of B is negative 2, and the value of C is 85. So the first thing we need is the value of B squared minus 4AC. So that's going to be negative 2 squared minus 4 times negative 0.05 times 85. And that's 21. No, that's part of your that's the determinant part of your derivative. So then remember, x is equal to minus b plus or minus the square root of b squared minus 4ac, and that's 21 over 2 times a. So that means x is equal to the opposite of negative 2, which is positive 2, plus or minus the square root of 21 over 2 times 0.05, or negative 0.05, is just negative 0.1. Now I'm going to see if I can kind of take a little shortcut here with y'all. Is the square root of 21 more than 2? Yes. Okay? So subtracting the square root of 21 from 2 isn't going to get me anywhere. Agreed? I'm going to get a negative number, and x being negative doesn't make any sense here. So I'm not going to do the subtraction, because that doesn't give me a useful answer. I'm only going to do the addition part. So if I take 2 plus the square root of 21 and then divide that by negative 0.1, my critical value is negative 65.82. Oh, wait. What did I do? Maybe I should know. Okay, yeah. Because when I said that, I forgot about that being negative. Okay, so that is a useless answer. However, if I do the subtraction, then I'll have a negative over a negative, which will give me a positive answer. So 2 minus the square root of 21 is a negative number. And when I divide it by negative 0.1, the answer becomes positive. That's a critical value I can use. Now, that critical value is bicycles. Okay? Does it make a bit of sense that we could make 25.825 bicycles? Well, we could round up and say we made 26, or we could say, well, actually, we only completely made 25. The question is, which one do we want to stop at? Probably going to be 25. So we're going to first assume the critical value is 25, but then we're going to use 26 as one of the test points. That way we're checking both of them. It can be anything. It can be a lot more or just a tiny bit more, as long as it's past it. Not that I'm aware of. I don't think I've ever had a problem. So here's our number line, and again, we can't make fewer than 0, so we're going to start at 0. And we don't know how many we're going to make, but we know that a critical value is somewhere around 25. Okay? So the only question we have left now, let's try making 1 and find the derivative. And then let's try making 26. And find the derivative and see what happens. So there is our profit function. We found our own derivative of profit, but this should be the numerical derivative of it without us having to type it in. So we're going to go to the table, and our test points are 1, 25, and 26. So at 1, the value of the derivative is 82.95, so that's positive. So it's increasing. It's going up. So we're going to the top of the hill. And we're happy about that, because that means we're thinking we're going to be finding a maximum, not a minimum. So then at 25, it says the value of the derivative is actually 3.75. It's still a little bit positive, but it's a lot less than it was. But at 26, what's the value of the derivative? Negative 0.8. So the derivative at 26 and past is going down. So that tells us that somewhere between 25 and 26, we got the most profit we're going to get. Okay? And it's better to make 25 than it is to make 26. So your maximum profit is from selling 26 bikes. And the amount of your profit for your 26 bikes is $1,229.60.
You mean sell 25 bucks?
25 bikes, I'm sorry, misspoke. 25 bikes.
Okay.
So you're going to sell 25 bikes for $1,229.60 profit. That would actually answer the question. Yes, Ryan. profit, if you look at your number table, and that is a good point, your maximum profit truly is for 26 because $1,231.10 is more than $1,229. Now, the thing to remember here is when you get those decimal numbers for your critical values, you want to round up and round down, okay? And if you build the table, what Ryan just noticed will tell you what your true maximum is. Because normally I would say, well, you need to make the 25th one. The 26th one's going to cause you to start losing money. Well, it's telling you that your profit is going down 80 cents on the next bike. So somewhere in between there, you actually did maximize some profit. Because remember, that Y2 is your derivative. And if it's in dollars, that negative 0.8 is 80 cents. So your profit is decreasing by 80 cents when you make the 26th bike.
Is it increasing right there from $25.6 by $2.50, you know, minus 80?
Yeah, you're still increasing a couple of dollars in revenue as you approach the 26th bike.
What would happen if you put it 27?
It's easy to find out.
Okay.
You're back down again. And if you go to 30, it's dropping even more. And notice on that 30th bike, you're down to over almost $20 less than the last one. Okay, so your profit's dropping fast. Okay? Now we have one more question to consider, and then I'm going to let you guys probably just go home. I'll probably tell you what we're going to do in Chapter 14, but I'm not going to actually have you endure the lecture, let's put it that way. So then the last question here, find the price that the company should charge to realize the maximum profit. Okay, so we're back to price. Here's your price function. And we decided the best value for Q was 26, right? Yes, it's the same problem. So the price is dependent upon demand, and that price is going to be the demand for 26 bicycles, which is 90 minus 26, which is $64. I can't even spell now. Huh. So it's $64 per bicycle. If they charge $64 a bicycle, they will realize their maximum profit. You will probably have a problem very similar to that one on the test. It might not be bicycles, but it'll be asking the same kinds of questions. So be sure you go back over this example, okay? The two topics that we're going to cover in Chapter 14, we're not covering 14.1, we're not covering 14.2, because we don't have anything that we absolutely need to cover in those two. What we're using Chapter 14 for is we're using it basically for applications, and there's two kinds of applications that we might run into. The one that we're going to do first is going to be something called elasticity of demand. How many of y'all have already had economics? Do you know what elasticity of demand is? So you've talked about that at length. You probably can explain what the meaning of it is better than I can, because you've studied it more recently. There is actually in calculus a formula for elasticity of demand, and that's capital E. And the way you find the elasticity of demand is you find the ratio between the price and the quantity. And then you multiply that by the derivative of the quantity with respect to price. We can set that up in the calculator too to actually show us what the demand is. The only thing to remember is that when you do this, that sign in front of that is going to be negative. Your demand is inelastic if E is a negative number, or is a number, not necessarily a negative number, but if E is less than 1. If the value of E is greater than 1, then your demand is elastic. And it has what's called unit elasticity when X is actually equal to 1. And then we'll talk about what all three of those things mean. But y'all at least have the benefit in this case of having some background knowledge of what elasticity is. The other topic that we're going to cover is another type of taking derivatives. So you get to learn a new derivative method called implicit differentiation. If you know how to take derivatives now, implicit differentiation isn't hard. But it does require some algebra skills. Sadly to say, this one is going to require probably that you do some simplifying. The only reason that we need those is there's certain applications where you have a function that doesn't only have an x in it, but it also has a y in it, and it's a function of both x and y. Okay? So we'll talk about that next week. Y'all have a good night. Go home, get some rest. Finish your 13.2 homework. Look ahead at 14.1 or 14.3, but don't really worry too much about 14.4. I'll explain it to you. Oh my gosh. I just gave her his homework. I'll have to take his test up there. I didn't realize I didn't give her his test.
Oh.
That's what that was.
Yeah.
Yeah, the videos are there.
Yeah, that's what I'm going to do. Thank you. You have a good weekend.
You too.
Thank you.